Hi, this is a little supplemental video I've made following on from my 8086 breadboard videos and writing Hello World and some of the changes I've made to the system. As you can see, when I press reset and let the reset go, every single time now it comes up and it writes Hello World. So it's working perfectly and writing the Hello World. I've made some changes in, obviously you can see that the LED is running so fast, you can't see how fast it's running. So I've made some changes to the way the 555 timer is set up. I've actually made a 100k resistor, which is this 100k resistor going to pin 7 from +5. And then I've added a 100k variable resistor, so I can actually change the resistance on this by changing the, by tweaking this, and I've put that between pin 7 and pin 6, and I'm using a 0.1 microfarad capacitor, and that's running the clock a lot faster, which is why when we hit the reset you can see it's very quickly writing the Hello World because the clock's running a lot faster. What I've also done is I've run the output on pin 3 from the 55 timer through my AND gate. I had this AND gate obviously to remember the reset signal. Well, I've actually then run that, which is this green wire running all the way down and onto one of the AND gates, and then I've connected the two pins together, and that's just to get a smoother output from the NAND gate, which I'm then using and running into the clock on the 8086. I've also connected a 0.01 microfarad capacitor on pin 5 of the 555 timer, and that's to reduce noise, so 0.01 microfarad capacitor. And that allows me then to run the thing a lot faster and get more consistent results when we just press the reset. Another thing I've done is I've added to the power rails a 0.1 microfarad capacitor across the power rails. Because this is switching very fast, and this power supply I have is just basically a USB supply to give me the 5 volts, or around about 5 volts. It's obviously switching so fast that it's pulling a lot of current out of the 5 volts. So I've put a capacitor across the rails there. So this 0.1 microfarad just sits between the positive and negative rails. I've added it here as well across the positive and negative rails, and here and here and here, and that and at the top rail there as well. So that just smooths and helps smooth the current and keep the power supply rails high. One other thing I've noticed was I was getting particularly funnies on the display. So when I looked up the datasheet, it actually says that when you're adding this variable resistor, which you adjust the contrast, I've actually added this +5 to 1 side of the variable resistor. I already had this one side of the variable resistor connected to ground, but I've actually also connected the other side to +5. So one side to 0 volts, one side to +5, and then the middle is still going across to the contrast on the actual LCD display, and that's made it a lot easier to change the brightness and the contrast on there. So that's just some of the little changes I've made to try to make the board work a lot faster and a lot easier and consistent whenever we set this. One of the other things I've added is an LED so that we can actually detect how our logic is actually working and whether it's going high or low. The problem is we've got outputs coming from the 8086 of read and write, and we've got the enable and we've got the I/O, and we might want to then check, is that I/O signal doing what we expect it to do? Is the logic gates that we've connected to, is the inputs and outputs doing as we expect? And so what I've done there is I've connected a little LED. You can see the LED is flashing as it goes high and low. The problem is, what I've done is I have an LED connected through a current limiting resistor of 220 ohms. Now, sometimes you can connect that, and what I've done is there's the LED connected there and the resistor there. the resistors in there to limit the current being pulled through that LED. The problem is there is a lot of current flowing through that 220 ohm resistor, and we connect it directly to the output ports of the 8086. That 86 is then either is pulling a lot of current, and it could then damage the gates, or maybe even the logic gates as well. So you need to be careful that you don't overload the chips by pulling too much current down through the actual inputs or outputs on the chips. Now, it actually is okay on the 8086 to drive the I/O directly to an LED with a 220 ohm resistor, and you can actually check that. The problem is when you then start to connect it into these logic circuits, it can then affect the way the logic circuits are working. So what you want to do is have some sort of non-invasive way of being able to connect your connection to the port to see whether it's 1 or 0 without it then affecting the way that the port is working. So what you can do is you can use what I've got as a FET or an FET. It is a gate, a drain, and a source. The one I'm using is this little small one, looks like a transistor, but it's actually a FET. It's a 2N7000. You connect this gate to your logic, to one of the ports, and it draws minimal current. And that's why I'm using a FET rather than a transistor. Sometimes can draw some more current, but basically the better bet is using a little FET, a FET. This is the flat face of the FET, and you have the source, the gate, and the drain when you're looking at the flat face, and then it's rounded the other end so you can tell which is the source, gain, and drain. The drain is just connected to the 220 ohm resistor and then through the LED. So the whole idea is if this goes high, this turns it on. So it effectively literally works like an electronic switch. So you put a high on there, it switches this on. So a high will switch this on, but turn the LED. A low there will then turn the LED off. So you can safely connect to any of your connections, like say this input here, just to see how this actually works and make sure that the input is actually working. And then when you reset, you can see whether that, so obviously it's pulsing there as it's going high and low. It's probably better if we were doing the single step through, so you could step through and see if the logic is actually working. So if you suspect there's something maybe wrong with the circuit, is my NAND actually working okay? Is the ALE signal is working okay? Is it going high and low as you step through? You can use this, and by connecting the gate then, which is the middle pin then to any of the outputs, you can just see whether they're going high or low as we run through. And it causes minimal current drain or minimal pull and doesn't impact in any of the circuits. Sometimes if you just connect that LED directly to the chip, it will actually then stop the chip from working, or the current drain on it will actually hold it low, or so you don't actually get to see how the circuit is actually operating. So that's why I use a little FET, and then you can use the gate. So if you've got problems and wondering whether's the logic working, you're stepping through, that's a great way to add an LED, and then you can simply go through and say, okay, is that gate high, or what's happening on that, without it then affecting the actual operation of the actual circuit. Here I've connected 3 LEDs, yellow, red and green. The yellow is connected to I/O, the green is connected to the right, and the red will light whenever it's not using the address in the range 80000 to FFFF. So we can see here that the I/O will come on as it's doing the out command. The red then goes out as it's not using the address in that range 8000 to FFFF, and then the green will come on to indicate a write. So you can see there the green is pulsing on and off, which is why we're using it for executing the commands that are on the display lines on the LCD. I run the post. Open the pod bay doors, please, Hal.